tutaj tylko kliknę i jedziemy. Okay, welcome, good afternoon, good morning, good night, wherever you are. Welcome to the next Tuesday seminar at the Warsaw University Astronomical Observatory series. Today we have an honor to host Joanna Drążkowska from Ludwig Maximilians Universität München. I cannot pronounce it properly in German. Sorry for this. She studied in Torun, but then she moved for her PhD to Heidelberg University. She also worked later at the Zurich University, and now she is in Munich, and she's an expert in planet formation. So we're going to hear from Joanna now, please.
Thank you, Łukasz, and thanks for inviting me. So in this seminar, I hope to explain how our understanding of the planet formation process has been changing in the last couple of years. So to start from the beginning, planets are formed in accretion disks that are surrounding young stars. And we call those disks circumstellar or protoplanetary disks. Those disks consist mostly of hydrogen and helium gas, with about 1% of heavier elements that condense out in the form of dust grains. And out of those dust grains, then planets have to form. And the whole problem is to understand how this exactly happens. So in so-called classical paradigm of planet formation that we had, that was developed in the 80s and 90s, it was thought that almost all dust grains are very quickly sedimenting to the midplane of such protoplanetary disk, and then they are forming the first gravitationally bound building blocks of planets that are called planetesimals. And this process of planetesimal formation was one of the problems because no one could really understand how this would happen. So this was more like an assumption that this planetesimal formation happens very quickly and pretty much everywhere in the protoplanetary disk. And then those planetesimals that were born a little bit larger than the others, they were growing very quickly in a process that is called runaway growth. And once this was over, the growth mode was changing to a little bit slower oligarchic growth. So the runaway growth basically meant that those that are born a little bit larger, they are growing much, much faster than the other planetesimals. And then our oligarchs were continuing to grow by basically clearing their direct gravitational zone of influence, so-called feeding zone. And then those oligarchs that managed to grow to large enough sizes within the lifetime of our gas in the disk, those could then start accreting the gas and become the gas giant planets. And then those oligarchs that didn't manage to grow fast enough and large enough, then they were left as rocky planets, so terrestrial planets. And then a big success of this classical paradigm of planet formation was that it was kind of correctly, for the standards of the solar system, predicting that the gas giants would form in the outer parts of the protoplanetary disk, outside of so-called water snowline. So basically the location where the disk becomes cold enough that the water can exist in its solid form as water ice. And now where does this conclusion was coming from? We just have to look at two very simple estimates. For the orange line shows us what is the maximum mass our oligarch can grow to by just clearing this direct neighborhood. And we see that this mass increases with the distance to the central star, because there is just more mass available, and also the size of our feeding zone is larger in the outer parts of the disk. And we have, of course, this steep jump that corresponds to the location of the water snowline. So we just have more material suddenly available. And then if we compare this orange line to our blue line, which shows us what is the minimum mass of a planetary core that we need to even start the process of accreting gas, then we find that this in turn is decreasing with the distance to the star. And that is purely because it is easier to accrete cold gas than to accrete warm gas in the inner parts. So the conclusion was that outside of the water snowline, we can form the gas-rich planets, while inside we should just have rocky cores. And of course, this was fitting very well to the architecture that we have in the solar system, with the gas giant being in the outer parts and this annulus of rocky planets in the inner parts. And there were some problems in this classical paradigm, such as mostly the time scale of the oligarchic growth that would lead to formation of the cores of those massive cores of gas-rich planets was very long. So for the core of Jupiter, it was already taking about 10 million years. And the lifetime of the gas disk is estimated from observations of other young stars to be at most couple million years. So it was already some tension, but it was thought that since we only have one solar system, we only know about one planetary system in principle at that time. Maybe there was something special that sped up the growth of our giant planets, and somehow the solar system was like in some privileged position to form like this. But then, of course, we found in the last years that this is not the case. We found from the statistical studies of the exoplanet populations that planet formation is extremely common process. So pretty much every time a star formed in our galaxy, there were some planets formed together with it. And on top of that, we also found that the planetary systems are extremely diverse. So for example, that we can in fact have gas-rich planets very close to their central stars, so actually closer than the Mercury is in our solar system. We have some Jupiter mass planets in some of the other systems, and also that the most kind of common group of exoplanets are those exactly in between the rocky planets in the solar system and the gas-rich planets of the solar system, and those are called the super Earths or sub-Neptunes. So all these discoveries then, of course, brought up the need for a universal theory of planet formation that will make it possible to explain the formation of the solar system, but also of those diverse exoplanets in one uniform framework. And this is something that we are now working on. And on top of this exoplanet revolution, there was another thing that has really sped up or showed the direction to our studies of planet formation theory. And this was the progress in the millimeter wavelengths observations of the young stellar objects. So here is what was basically the best image that we had of a protoplanetary disk 10 years ago. This is a disk surrounding a young star HL Tau. And that was basically just a blob of millimeter radiation that was telling us that there is warm dust surrounding this star, but not really much more. And then a couple of years ago, the Atacama Large Millimeter Array kind of came to life in its extended configuration. and provided us with this spectacular the first resolved image of a protoplanetary disk. And since then, we have been able to resolve even more protoplanetary disks. And we learned that pretty much every single disk that we are able to look at with high enough resolution is showing us some substructure. Mostly these are axisymmetric substructures in the form of dark gaps and bright rings, but some disks look more like some spiral type substructure. So if you look now at the literature concerning these ALMA observations, most often these signatures are interpreted as signatures, the substructures are interpreted as signatures of planet formation. Why is that? It is because if we make a model of a protoplanetary disk and we insert large enough planets into our model, then we find that this planet is carving a gap both in gas and dust, and it is also acting as sort of a barrier for dust, so that the dust is collected just outside of the planetary gap, and it is forming this bright annulus, right? So that would correspond to those rings that we observe. So this is the most kind of believed interpretation of these substructures. There are, of course, other interpretations. So in 2019, we proposed yet another way to look at this and to treat these bright rings as signatures of ongoing planet formation, because the people that made this DICHO study, so the one with many resolved protoplanetary disks, they also found that if they measure one particular property of each of those bright rings, which is called the optical depth, then they find that every single ring falls into pretty much the same regime of the optical depth, which is with the values of about 0.5. And then if we make models in which now this is 1D model, right? So we just have the distance to the star. We assume that this is axisymmetric, and we insert a planet here. And the planet interacts with dust such that, again, this bright annulus of dust is formed outside of the planet location. We found in our models that basically we're reproducing one of the rings of HD 163296, which is somewhere here, that if we don't do anything, we just put a planet and we have the dust there, then the optical depth of our ring will quickly grow to higher values than those that are observed. So to reduce it and to keep it within the observed range, we have to take out some dust out of this annulus, and we have to transfer the dust to gravitationally bound objects, which are called the planetesimals. And I will talk more on how we see the planetesimal formation process today later in this talk. But the important thing is here that the models of planetesimal formation that we have now are exactly then producing the annuli such as those observed with ALMA. So we can treat these optical depth values as sort of indirect evidence for ongoing planetesimal formation. And those models that I showed here in the last two slides are illustrating very well one of these conceptual changes that we had. That is that planets and dust coexist in protoplanetary disk. So it is not like in this classical paradigm of planet formation that where most of the dust was extremely quickly bound into gravitationally bound blocks. but it is rather that planet formation is a local process. It only happens somewhere in the disk, and the rest of solids is left in the form of dust. And this is actually connected to another huge development that we have in planet formation theory in the last years, which is the concept of pebble accretion. So pebbles is just dust aggregates of the sizes of roughly millimeter to centimeter. And it was found in theoretical work that for a planetary core, it is actually better to accrete pebbles than to accrete planetesimals. And this is because of the interaction between pebbles and gas that is helping the pebbles to settle onto the surface of this planetary core, while planetesimals often get deflected by gravitational interactions. And what is more, in the pebble accretion scenario, the size of our feeding zone now increases. So I told you that these oligarchs in the classical view could just accrete the solids within their kind of direct neighborhood, so where their gravity was reaching, while the pebbles are mobile, so they are drifting through the disk. And because of that, the size of the feeding zone increases because the planet can just sit somewhere and wait for the pebbles to come even from the outer parts of the disk. So why is this the case? Why are the pebbles moving through the disk? To understand that, we have to look a little bit closer at the physics of such an accretion disk that is surrounding our star. So if we now follow a portion of gas that is located somewhere in our circumstellar disk, and we want to know what is the orbital speed of the gas, we have to take into account three factors. So there is, of course, the gravity with the central object, there is the centrifugal force, and there is pressure because the gas is pressure supported. And the pressure is generally decreasing with the distance to the star because in the inner parts, the disk is denser and hotter. So from this force balance, we are getting the rotation velocity of gas, which is slightly lower than the Keplerian velocity. And this factor, but by which it is lower than the Keplerian velocity, we call it eta, and it's typically below 1%. So this is a really tiny difference between the Keplerian rotation and the gas rotation, but it is already very important for our dust grains, because if we are now a dust grain and we want to be on a Keplerian orbit, we see that all the gas molecules are going against us, which we call the headwind problem. And because of the aerodynamical interactions between the gas molecules and our dust grain, the dust is losing its angular momentum and has to move inward towards the star, which is called the radial drift. So now the radial drift is basically what makes the pebbles mobile. So the speed of the radial drift depends on the size of our solids now. But of course, in the theory, we prefer actually to parameterize the size by so-called Stokes number, which is just the ratio of the stopping time, which tells us how quickly the gas is interacting with the dust, and the orbital time. So it's just most of the time is directly proportional to the grain size. So now on the left-hand side, we have very small dust grains that are very well coupled to the gas and are just moving together with the gas accretion flow. On the other side of the spectrum, we have very large solids, so our planetesimals, that are pretty much on Keplerian orbits and they don't really drift. But we have this intermediate regime, which is exactly where the pebbles are of the dust that is kind of starting to decouple from the gas, and for which this interaction with subkeplerian gas leads to the fastest radial drift. So now if we make some models, we will be now looking at the radial redistribution of our solids. So I am plotting here the surface density as a function of the distance to the central star. AU is the astronomical unit for those of you who don't know. And 1 AU is on average where the Earth is in the solar system. And now when we make the models with the radial drift, we find that the outcome depends a lot of what is the size of dust grains that we assume. So now on the left-hand side, we will have models where I assume that all the dust grains are of 1 millimeter and this size is fixed. And on the right-hand side, we will have models that includes the full prescription for dust coagulation, so for how it grows in our disk. And then when we run these results, we see that it is quite different depending on what we assumed. So for these 1 millimeter sized grains, the disk is cleared from the outside, where those 1 millimeter grains are already well decoupled in the outer parts of the disk, while they are still kind of coupled in the inner parts. So kind of we get this temporary pileup, and then everything is gone. While in the dust coagulation model, it's kind of a different picture of more homogeneous depletion of the solids from the disk. So why is there such a big difference? Well, it is because the dust coagulation doesn't really keep all the grains at the same size. It is more complicated than this. So the outcome of dust coagulation depends on what are the collision speeds between different dust grains, but also on what happens when the grains actually collide. So what are the collision outcomes? And for the collision speeds, this is something that we just calculate in our models. So this comes from the theory, but the collision outcomes, for that, we actually need some laboratory experiments. And we have groups that do such experiments here in Germany. So they use vacuum chambers that are put in microgravity conditions to simulate this sort of pre-planetary dust analogs. And the most like zeroth order conclusion, simplifying all these experiments that they are doing, is that if we collide our dust aggregates with low velocities, so here it's 9 millimeters per second collision, then our dust aggregates will stick. While if we increase the collision velocity, then we reach a point in which the collisions are not leading to sticking anymore, but they are more like catastrophic collisions, like here already at 7 meters per second velocity. So then in our dust coagulation models, we use this parameter that is called fragmentation threshold. And that basically is our boundary between the positive collision outcomes and then the negative collision outcomes. And you may remember from the slide on radial drift that the radial drift alone was producing velocities up to 30 meters per second, so much higher than this fragmentation threshold velocity. So when we look at the typical outcomes now that we get in our dust coagulation models, then we will be actually looking at, again, the distance to the star. So with 1 AU being the Earth location and the grain size on the y-axis. And we start this model with all our dust that is put at sub-micron sizes, which is what we expect in a very young protoplanetary disks, what the dust is there. And then the color coded is the density of dust, right? So the darker it is, the more dust we have at a given location and a given size. And when we run this model, we see this inside-out growth pattern. It's just because closer to the star, everything happens a little bit faster. And then those lines are our analytical prediction for the fragmentation barrier with the orange line. And here I already chose a very optimistic fragmentation threshold of 10 meters per second. And the drift barrier, which basically means that outside of this line, the drift is faster than the growth could ever be. So that's why nothing can go past this barrier. So in this kind of typical model, the maximum grain sizes that we get are 10 centimeter. So how can we ever even form any planetesimals this way, right? When we have the fragmentation and radial drift, that is still a problem. That was the problem in the classical theory of planet formation, and it is something that we really have solved rather recently. And it seems that the solution is a process that is called the streaming instability, which is a hydrodynamic instability that pretty much turns pebbles into gravitationally bound planetesimals. So we are kind of starting with something that we can still grow to in our models, but then we are jumping all those problematic stages where the radial drift is too fast and the collisions are too fast, and we form large planetesimals. So here is the animation where we are looking at the density of pebbles. And if you look closely, you will see that this is already starting with some sort of perturbation. And this is what the streaming instability needs, because the streaming instability essence is that this configuration of the interaction of dust and sub-Keplerian gas is unstable to local density perturbations. So if we start with some filaments, then those filaments will increase their density and they will fragment into those clumps. And then some of those clumps will be so dense that they just will be gravitationally unstable and they form planetesimals. And again, if you look closely, you will see some binary planetesimals, so that are kind of rotating around each other. And this fact that the streaming instability forms many binary planetesimals is now seen as a proof that it was the streaming instability that triggered planetesimal formation in the solar system. And this is because if we look at the comets or at the Kuiper belt objects, like here the Aracot object that we sent the NASA New Horizons mission to, many of them are binary. And that's not it, because also from the Kuiper belt studies, we see that the rotation direction of those binary objects fit very well with what is seen, what is predicted from the streaming instability simulations. So roughly 80% of the Kuiper belt objects have prograde rotation, and this fits very well. So it is seen as a proof for the streaming instability. So now the biggest direction kind of my own studies was to find the connection between the dust evolution models and the models for the streaming instability. And the key point here is that the streaming instability needs increased dust to gas ratio. So I told you at the beginning, the default kind of value for a young protoplanetary disk is that the dust to gas ratio is about 1%. But the streaming instability needs actually a little bit higher dust to gas ratio to start forming planetesimals. So my studies have shown that one of the locations that is very good for streaming instability is actually this special place that I already mentioned in this talk, which is the water snowline. So the place in which we naturally get the increase of solid abundance already at the beginning, right? Because this is where we can have the water ice. But this is not it, because for many years, the laboratory experiments were telling us that they expect that dust aggregates that have a lot of ice will be more sticky than dry aggregates. And if they are more sticky, that means that they grow to larger sizes and they also drift much faster than the aggregates that are inside, which leads then to kind of a global traffic jam effect, because those large aggregates arrive at the water snowline and then they evaporate and they stay at smaller sizes. So those cannot be removed that quickly by the radial drift. So we kind of build up the abundance of solids. And that's still not it, because there is another effect that helps us, which is called the cold finger effect. And it basically relies on the outward diffusion of the water vapor that is delivered, right, by the water-rich aggregates. And then the water vapor from inside of the snowline is diffusing outwards, and it's recondensing on the dust aggregates that are just outside of the water snowline. So we get another bump of the solids abundance just outside of the water snowline. So the cold finger effect is actually a very fast effect. So the timescales of these diffusions are something like the orbital timescales. The traffic jam effect takes much longer because we have to wait for the dust aggregates in the outer parts of the disk to grow to larger sizes and to drift. But actually the traffic jam produces higher enhancement of the solids. That's at least what I found in this paper that I published in 2017. And now if we put all of the things together, so we put models of dust evolution and planetesimal formation in this streaming instability prescription, and then we start with no disk yet at all. So we start from the moment that the molecular cloud is only building our protoplanetary disk. That's why this plot is empty. We will be looking at again, at just the surface density distribution with the radial distance. And on the bottom panel, we will be recording the history of planetesimal formation in our model. So now if we play it, we are building our disk from inside out, and then we let our disk evolve. And in red, we have this planetesimal population that is forming. And you can see here on the bottom panel that indeed the planetesimal formation follows the water snowline, which I marked here with the bright blue line. And we see that planetesimal formation is actually a continuous process, it's not a burst. And this is another conceptual change that we have with respect to this classical view. And this is turned out to be actually extremely important. So in these models, thanks to this cold finger effect that is very fast but not very efficient, we form a little bit of planetesimals already very early during this infall stage, so when the protoplanetary disk is only being built. And then we form much more planetesimals thanks to this traffic jam effect. And it turns out that these two things that we have is that planetesimals form at the water snowline, and some planetesimals form very early, and then others form later. These two things kind of find confirmation in the meteoritic records that we have from the solar system formation. So we managed to show that and to get this published in Science earlier this year in the paper that was led by Tim Lichtenberg from the University of Oxford, that this scenario with two bursts of planetesimal formation at the water snow line is what we see in the solar system, what potentially explains the solar system formation. So what is the deal here is that we know that the solar nebula was enriched with short-lived radioactive nucleids, and those nucleids, if we trap them inside of planetesimals and they decay there, they lead to heating, right? So they heat up our planetesimals, and mostly aluminium-26 with the lifetime of 0.7 million years is particularly efficient. So now if we form some planetesimals here, they will basically experience orders of magnitude more heating than planetesimals that are formed later. So now what we did here was basically to process the planetesimals that we formed in my previous models with the models of internal evolution of such planetesimals, including the heating by aluminium-26 decay, and then planetesimals that are in this reservoir 1, so the ones that are formed very early, they heat up a lot. So streaming instability mostly leads to very large planetesimals with roughly 100-kilometer radius. So they will be here. And then this will mean that they will dehydrate, so they will lose their water, but also the rocks will melt and the iron will rain to the center, right, and will form the iron core. And for planetesimals that form later, so in this reservoir 2, they won't really go through all this in such a high rate. So now if we compare the results in terms of when our planetesimals formed the iron cores, which is something that we can measure from the meteorites, we see that our planetesimals in reservoir 1 correspond very well to meteorites that are from so-called non-carbonaceous reservoir. And then our reservoir 2 will correspond with this carbonaceous reservoir. So the deal with those two reservoirs, why do we divide all meteorites into two reservoirs, is something that is also a big development in the geochemistry community in the last years, where it was found that if we measure with a high precision the abundances of various isotopes in meteorites. So the precision here is something like parts per million, right? And then we plot every single meteorite that we can measure on such diagrams. They always fall in either of those two groups. So there is nothing in between. We have two distinct reservoirs that the meteorites are coming from. Also, the Earth and Mars and Moon are falling in one of those reservoirs, which is this non-carbonaceous reservoir. And this is called the Great Isotopic Dichotomy. So the cosmochemistry community found or proposed that the solution for this dichotomy is that the Jupiter formed extremely early in the solar system and opened the gap and prevented mixing between the materials from the inner part of the solar system, which then would correspond to this non-carbonaceous reservoir, and the outer part of the solar system, which would correspond to this carbonaceous reservoir. So today, the meteorites are mostly coming from asteroids that are all located inside of Jupiter. But of course, this mixing of asteroids might have happened later. But what we show so the problem here is that there is no model, even with this pebble accretion speed up, there is still no model that could grow Jupiter so quickly to really provide this split. So we show in the science paper that a more natural explanation for the isotopic dichotomy may be just this burst of planetesimal formation in reservoir 2. So basically that we show that this planetesimal formation that is so efficient in the later stages is enough to prevent mixing of these reservoirs. So that seems to be just more consistent with a general picture that we have for planet formation. So another key thing in this science paper is that you see that all the planetesimals, so all the building blocks, are initially formed water-rich, and this dichotomy between dry planets and water-rich or gas-rich planets then arises not because those planetesimals formed closer in, but because they formed earlier, right? And they inherited more of aluminum-26. And we think that this is actually an explanation that will let us form diversity of exoplanets if we start with slightly different budget of aluminum-26, because you may imagine that maybe some other circumstellar disks were not so enriched with aluminum-26. So even if they formed planetesimals early, those planetesimals wouldn't really lose all the water. So I am with this at the end of my talk. So I hope that I convinced you that planet formation theory is really exciting topic that is undergoing a lot of changes now. And I hope that you remember the streaming instability and the pebble accretion, which are the most important developments, so to say. And they both rely on how efficiently dust can grow to pebbles. Yeah, so that's pretty much it. If you have any questions, I'm happy to answer.
Okay, thank you very much, Joanna. I'll do the clapping on behalf of everyone. Thank you for a very nice talk. And now for the question session, that's what we normally do. If you have a question here on Zoom, please raise your hand like Przemek just did. Przemek, please.
Hey, can you show the first slide about solar system formation, about the location of planetesimals?
This one, or
maybe one of the areas earlier ones. Okay, this one. So most of the planetesimals that you show form like relatively close to the sun, like 5 to 10 to 20 astronomical units of the sun, whereas we have two ice giant planets in the solar system, Neptune and Uranus, which are 20 to 30 astronomical units. So how did it form?
So the kind of most accepted paradigm for solar system late stage, so after the gas disk dispersed, is the Nice instability model, which basically the initial condition of the Nice instability is that the 4 or actually maybe even 5 gas giants were packed more closely than they are now. And after the gas disk dispersed, there was this kind of big instability that put the giant planets where they are now at. And one of the signatures we believe that we have for this instability are the craters on the moon, where we see that the inner solar system at some point was bombarded with asteroids, kind of coming from the outer parts. So yeah, this is something really my research doesn't really cover these late stages, but actually it seems to be quite consistent that we form planets a little bit closer than they are, at least the giant planets that they are now.
Okay, thank you. Any more questions? If so, please raise your Zoom hand. Radek, please.
Thank you. Very nice talk. I'm really impressed by these last results. I have one question, but first I would like to ask you to go back to the slide from your 2018 paper with the animation. I really like the animation, so I just want to watch it for some more time. And the question I have is, you said you're not working on the late stages. How do you define the late stages of formation? Is it like 5 million years, 10 million years?
Yeah, it's a good question, because in the classical paradigm, it was very easy, because early stages was dust to planetesimals, right? And then the late stages were where you already had the planetary core, and then the planetary core is growing and migrating, right? Because that's another thing, that we have the planet migration now, that the planets are also moving. So yeah, so I think the definition is early stages is if you start your model with the dust, that's the early stage. But yeah, actually it's a good question, that here on this plot, right, then the late stage will be probably something after a couple million years, where you already formed some planetary cores.
Good. Any more questions to Joanna? Eva, please.
Okay, great, very, very nice indeed. Thanks a lot. And I'm working for a little bit different part of the formation of the planetary systems. So I would like to, your period is earlier than mine. So I would like to understand, I mean, how can the way in which you are form planetesimals then can influence how they behave later on? Because, I mean, in a sense, what was a little bit missing here, it's this, you mentioned this a little bit later on in the question part about the migration. Migration is an inevitable process which takes place if you want or not. And it is important when the object will have sort of more than 1 kilometer in diameter. So, I mean, it's not really for planetesimal as such, but for planetary cores. So how your planetesimal period of creation can influence what will happen later on, and how this influence the planetary cores.
So actually, for the science paper, we of course had to discuss everything. So we have been able to show that at least for the terrestrial planets' cores, in fact, their migration already will be significant, but we'll let them always stay inside, right, of this water snow line. But I agreed, or I think actually that the migration of Jupiter and the giant planets, that's something that we don't really understand about the formation of the solar system. I'm not actually sure if planetesimal formation changes the planet migration. I think it is definitely the dust evolution can influence planet migration, because the dust provides the opacity, right? So it kind of regulates the cooling of the disk. And some people show that, for example, the water snow line may be not just the barrier for dust, but also for planet migration because of this change of opacity. So yeah, I think this really requires some more like a wider view, where one would be calculating the properties of the disk consistently with the dust growth model, but also then calculating planetesimals consistently, right? Because in our view, the planetary cores don't form everywhere. So we find it extremely unlikely that a planetary core will form at 50 AU or at 40 AU, where it would kind of need to form in the current migration models that start the Jupiter core at 40 AU, so that it ends up at 5 AU where it is now. So yeah, I don't really know the good answer to this.
Oh, thanks a lot. And if I still can keep track with this migration, because as you for sure know very well, I mean, we have quite wide class of planetary masses where the migration is really not, it's not known. I mean, it is also in recent years we discovered that, I mean, the type 1 migration, type 2 migration is very simplified way of thinking about what is going on. And I mean, of course, this kind of assumptions done in many models are necessary in order to do some step forward. But I mean, that's not what planets which are opening the partial gaps, it's not what they are doing. So I mean, this very, there is uncertainty of how the planets with partial gap opening, how they migrate. So that's why, I mean, if you still can comment, how, if we will know, I mean, how robust is, I mean, the results if you change the migration rate. I mean, can you have a sort of different results, or I mean, it will sort of not change very much? How sensitive to the knowledge of migration is the results which you have presented in science paper?
No, I think it is very sensitive, yeah, because we basically neglect here the migration for Jupiter, right, at all. Like we basically don't really discuss what happens later. And for the terrestrial planets, yeah, we show here, which is like this kind of outcome space. So when we varied some parameters, that it still kind of stays roughly where it should be. But of course, if we then change it drastically, with something that we don't take into account here, then yeah, of course we can lose those planets, right?
Okay, thanks a lot, great.
Okay, thank you very much. I don't see any more questions. So let's thank Joanna again for this very nice talk. And I will now and thank you all for joining, of course. And I will now stop all the recordings and the YouTube transmission. But if people are willing to stay here online, I will not be closing this window for a few more minutes for less formal chat, maybe in different languages. So thank you all for joining, and see you next week.